Last topic in Physics 20. Okay, Doppler effect. Right? Now, we're going to go over what the Doppler effect is. We're going to go over how it happens, and then we're going to look at some problem solving to do with it. Okay, using the Doppler effect formula. Okay, we will actually be using a slightly modified version of the Doppler effect formula because you guys actually only have to deal with Doppler effect problems that involve a moving source. Okay, in actual fact, most Doppler questions involve either a moving source, a moving observer, or both. Okay, which actually doesn't make them a lot harder. I don't know why the Alberta had decided they didn't want to do those because they become more interesting. But anyway, you only have to deal with ones that have a moving source. Okay, so it is the source of the sound waves is in motion. That's the type we'll be dealing with. Okay, all right. So we're going to look at how the Doppler effect changes the pitch of a sound. What wave characteristic is associated with pitch? Frequency. What did we say about frequency? That it can't change. How can this cause a change in the pitch then? Well, the answer is it actually doesn't. Okay? The pitch of the wave, the frequency of the waves doesn't change. We simply encounter them at a higher rate than they were produced because the source, or ourselves, are moving. Okay? This is how you get a speeding ticket. Okay? It's how radar works. Okay? When you are driving your car, okay, if you have radar positioned here, okay, the waves go out at a certain wavelength, frequency, and speed. Since you are driving into those waves, okay, they bounce off of your car at a faster rate than they would if you were stationary. If they were stationary, they'd just hit your car, bounce back. Their frequency, wavelength, and speed would all be the same. Since you're moving into them, you hit them more often than you would if you were stationary. Agreed? Every time you hit a wave, it reflects off of you back towards the emitter. When the waves get back to the emitter, they're now all of a sudden like this, because you pushed them back that way. Okay? You encountered them at a faster rate than you would have if you were stationary, and the little computer thing inside the Doppler gun, okay, can calculate how fast you're going based on that. Okay? That's how you get a speeding ticket using radar. All right? There's really no way to thwart that unless you have sufficient funds to build your car out of the stealth materials they make the stealth bomber out of. And if you had that kind of money, I think you'd just get a ticket. Because you have bottomless money because stealth bombers cost $2 billion. Okay? Yeah. So there's really no way to get around that. Okay? There's really no way to avoid it. Laser, radar, whatever. Okay? They're all going to work the same. And of course, they have these things that you can buy in certain places. Radar detectors, laser radar detectors. They're going to save you from a speeding ticket. They might save you from a photo radar ticket. But if this is an active, police vehicle where they're actively running a speed trap, the only reason your radar detector goes off is because the radar gun was pointed at you. Okay? All your radar detector is doing is telling you you're getting a ticket. Okay? The only time it might work and save you from a ticket would be if it was a photo radar thing where the radar is always on and not necessarily pointed at you at that particular time. Okay, but now with the modern radar systems, especially the laser, okay, the laser radar, it's tight beam. If your radar detector goes off, it's because you got hit. Okay, you are getting a ticket at that point. It doesn't spread out like the radar used to. Okay, and the last thing we're going to look at is how the Doppler effect is responsible for the sound barrier. How many of you have heard of that term before? Okay, sound barrier. All right, so we're going to look at why that occurs and how it's actually a result of the Doppler effect. Haley, can I get you to let whoever that is in? Thank you. All right, but first, I'm going to play for you Sheldon Cooper's explanation of the Doppler effect. All right. So, Doppler effect, like we said, is the change in frequency because the change in frequency detected by an observer because either the observer or the source of the waves is moving. Okay, and how they're moving affects how the sound is perceived. Okay, in the case of the fire truck and the horn that we just saw, okay, we had a vehicle that was approaching the source of the waves. Okay, was the source of the waves and was approaching the observer. So what happens is the observer in front encounters the waves more often than a person would if the train was sitting still or the fire truck was sitting still. Okay, so as the train is approaching, it's producing waves of a certain frequency. If the train was stationary, those waves would be a certain distance apart. But because the train or the fire truck is moving, those waves don't get as far away from it as they should, because the source is also moving as it produces them. So what happens is the waves bunch up in the front and they spread out in the back. So when the train or fire truck is approaching me, I hear a higher frequency or a higher pitched sound because the waves sound like they're closer together. Okay? Their frequency is actually still being produced at the same frequency this train was if it was stationary. But because it's moving, I detect them differently. Okay? Same as when it passes me. When it passes me, it produces a wave and then runs away from it before it produces the next one. And so it makes it seem like their frequency is lower, even though it isn't. Okay? It's just perceived that way because either the source or the observer is moving. Okay? This would be even worse if the train and the observer were moving towards each other. If they were moving towards each other, then that change in frequency would be even greater. Or perceived change in frequency would be even greater. Okay? If they were moving along both in the same direction at the same speed, what would that person hear? Normal frequency. Yeah. Okay? It's about the relative change in the observer and the source of the sounds.
Wouldn't you hear it from behind you because the actual station forward?
The frequency wouldn't be different. Okay? You wouldn't hear it as clearly because the siren is facing away from you now. But it's the fact that it's moving away from you that makes the frequency change.
Is that why it sounds different?
No. The reason it sounds different is because it's moving, not because the horn is facing forward.
If you had a higher frequency, would you be able to tell the Doppler effect is happening?
Yes. Yeah. The actual frequency makes no difference on the effect of the Doppler effect. The Doppler effect affects all frequencies equally.
Would you be able to hear it more if it was a higher frequency?
Not really.
Lower frequency?
Not really. Right. You would and that's part of the reason we can instinctively tell if something is moving based on its sound. Right? We instinctively know if something sounds kind of strange that it's actually in motion and actually moving towards us or moving away from us. It's just something that we understand at an instinctive level. Okay? So that's kind of how that works. Now, that's important if we're talking about anything moving at close to the speed of sound. Okay? So what happens is, if you've got a plane that's moving, planes make a lot of noise. Okay, they have big motors, especially jet engines. Okay, are very, very loud. Right, we're looking at hundreds of 130 decibels, enough to shatter your eardrum. Okay, so when they're moving, they make a lot of noise. When they move very fast, that noise builds up in front of the plane. Now remember, sound waves are a series of compressions and rarefactions. So there's areas of compressed air and areas of rarefied air, kind of stretched air. Okay, that's how sound works. But if I'm moving at essentially the same speed as the waves I'm making, what are they not doing anymore? Yeah, they can't get away from me because I'm going the same speed they are. So I keep making these compressions. I keep compressing this air, and it can't get away from me. So it builds up in front of me and becomes incredibly dense. Right? And that's what creates the sound barrier. Right? The sound barrier is a wall of incredibly dense air that builds up in front of an aircraft that's moving at the speed of sound, or close to the speed of sound. Okay? And so this was a big problem back in the very early days of the space race. Okay? So back in the late 40s, when jet engines were just being developed, okay, they were getting planes to go really fast, way faster than the propeller-driven aircraft could go. The problem was that no matter how powerful they made the jet engines, the planes couldn't go faster than the speed of sound. Anytime they started approaching the speed of sound, they would get shaken apart. Literally, they would break apart. Okay? And that's what kind of made this term, or coined this phrase, the sound barrier. Okay? Because they just kept building more and more powerful aircraft and telling the pilots, just crank that thing up. Okay? And these things would look like they smashed into an invisible wall in the sky. They would just be roaring along, and then all of a sudden, boom, that was it. Okay? And before they would explode, the pilots would report that it was getting really turbulent, the plane was feeling it was shaking itself apart, and that's literally what would happen. Okay? They would run into this incredibly dense wall of air in front of them that was their own creation, and it would shake the plane apart. Okay? Kind of following me on that one? All right. So the only way to break the sound barrier is to have a nose on the aircraft that has the right shape, so that it can create a disturbance in this wall of air that's building up in front that the plane can pass through. Okay? Once you can pass through that wall of dense air, then suddenly all of your sound waves are now doing what? They're falling behind you. Nothing builds up in front of you. Okay? The day the sound barrier was broken for the first time, the maximum speed of a human being doubled. Okay? Because everyone could go like around the speed of sound, and suddenly when they got through the sound barrier, there was nothing to resist this rocket-powered aircraft that they could do. Okay? Because this was the mindset of the people trying to break the sound barrier. More power. More power, good. More power means go through barrier. Okay? And they would just keep building these more and more. They got to the point, the plane that actually broke the sound barrier for the first time was dropped out of the bottom of a bomber. Okay? It was a rocket-powered aircraft. It only had a rocket engine on it. It didn't have a propeller, it didn't have a jet engine, it was a big rocket. And all they were going to do was light that candle and drop that thing out of the bomber, okay? And the pilot was going to fly it into the wall. Okay? Except that they had put this weird little needle, well, not little, it was actually quite big, on the nose of this aircraft. Okay? And the idea was that this weird nose cone shape would disrupt the air in front of the aircraft, allowing the aircraft to pass through the sound barrier. Okay? And that's exactly what happened. And once it did, this rocket just fired the plane to an incredible acceleration. It literally jumped from Mach 1 to about Mach 1.6, like that, okay? Because it had so much power. Okay? And the weird thing was, because everyone on the ground thought it had been a failure. Because they're watching this plane, and as it breaks the sound barrier, there's a puff of water vapor that looks like the plane is exploding. And then there's this cracking boom that they hear a few seconds later. The sonic boom. No one's ever heard one before, because no one's ever gone faster than the speed of sound. So we're going on the ground like, oh crap, back to the drawing board. Okay? There's another pilot gone, and they would tell his wife and kids, and everyone was kind of bummed out because they thought they had it all figured out. And then about a minute later, the pilot comes over the radio and is like, what do you guys want me to do? I'm going really fast. And they're like, shut the engine off and land that puppy. We got to figure out what we did right. Okay? And so he landed the plane successfully, okay? And from there on, we were able to build aircraft capable of going faster than the speed of sound. Now, do we build a lot of aircraft that go faster than the speed of sound? No. It's incredibly hard on aircraft to do that. Breaking the sound barrier is a violent act, okay? And it puts a lot of strain on the airframe of an aircraft. So we don't generally build too many planes that do it.
When you hear anything, would you hear this?
If you're in the plane, you'll feel it rather than hear it.
So you won't hear sound?
No, you hear sounds because the air in the cockpit is moving with you, right? And so it's a relativity thing. Okay, you still hear the sound of the engines because that's vibrating in the plane, and you can pick that up. Okay, you would feel and sort of hear the sound barrier being broken, but not like people on the ground would hear it. Yeah. All right. Now, when the aircraft passes through the sound barrier, you always get these clouds forming around the plane. Okay? Because how many of you have taken Chem 20? Okay, you know the ideal gas law, Charles' law, Boyle's law, you know the thing about when you put pressure on the gas, you can turn it back to a liquid. Okay? So, what happens here is there's so much pressure on the air in front of the aircraft that it will push water vapor back into a liquid state for an instant. Okay? So the pressure builds up in front of the plane, we get all this water vapor condensing back into a liquid, and then when the plane pops through the sound barrier, that pressure is suddenly released. That's the boom. And then the water goes back to being a vapor right away. So the cloud appears and then disappears really quickly. But there's always a cloud like that when the plane breaks the sound barrier. Okay? All right, so show you the videos here on the sound barrier. Okay, so what we can see there is obviously that all that water vapor, all those gases really get compressed, okay, as that air gets compressed in front of a supersonic aircraft. okay, or in this case, like a slightly subsonic aircraft. It hasn't quite gotten through the sound barrier yet. Okay, so we get that boom. That boom is an overpressure, and it's just released very quickly, which is why it's so loud. Okay, now of course, when people were first started breaking the sound barrier, and they got this loud pressure wave, the immediate thought was that could be used as a weapon. If you flew really low over the ground, over a target, broke the sound barrier right over top of it, you could, the pressure of the pressure waves would knock things over and like throw soldiers out of trenches and things like that. People are like, oh, we'll do that. And pilots were like, are you nuts? Do you realize how close to the ground we would have to fly in order to do that? And we would certainly get shot down, because it's kind of hard to sneak up on somebody in a plane when you're just going the speed of sound. Okay? If you're going faster than the speed of sound, then you could sneak up on somebody. Okay? You in fact could fly right over, and then the sound would follow you. Okay? But it wouldn't really work very well because you'd have already released the boom. Okay? You actually have to break the barrier right over top of your target in order for that to have any effect, and the effect is negligible. Okay, that pressure is released so quickly over such a large volume of air that the effect of it dissipates really, really fast. The Mythbusters actually busted this one. They built like a replica house and had an F-18 fly as low as it was allowed to over top of this thing and break the sound barrier, and they only managed to like knock a dish off of a counter. Okay, in this playhouse that they had built. Didn't break any windows, nothing. Okay, so it's just not that huge of a pressure release. It's loud, but it's not like damage.
So let's say you go faster than like the speed of light, even though it's not happening, but like, would there be a big light boom?
Well, there'd be a flash. Wouldn't be a boom, right?
And so it'd just be super bright.
Something like that, maybe. Except, remember, light waves are not longitudinal, right? They're transverse. So it probably wouldn't have the same effect, because the waves, I mean, I guess they would sort of pile up in front, so there might be a flash, but not a boom. No one will ever know. Okay. So we were talking about the Doppler effect here and the effect that this can have. Okay, we only really perceive the Doppler effect with sound, right? Things would have to move really, really fast for us to notice that Doppler effect with light, okay, like for it to be actually noticeable to our eyes. Obviously, the effect is useful for radar, okay, that's how radar works, okay, but we have to have a pretty sensitive instrument to be able to detect the changes in the radio waves that a radar gun would produce, okay. So, everyone kind of follow me on that? Okay, but it would also work for light. Now, the fact that the Doppler effect does happen for light is why we know that the universe is expanding. Okay? The universe is expanding, and we can confirm this because as we watch things that are very far away, their light tends to be shifted towards the red end of the spectrum, meaning they're going away from us. Okay? So we can kind of detect that. And we also use it, earlier on, we were detecting like other planets around other stars. We were using a Doppler effect thing to do that. Now we have better telescopes that do it differently. But what we would watch would be a star's, the wavelength from a star would change. Sometimes it would be shifted blue, sometimes it would be shifted red. And what that would mean is that the star was wobbling back and forth. And the only thing that could make a star wobble back and forth would be something orbiting it that was pulling on it. And we could use that wobble and that change in wavelength to detect how big the object would be, how far away it would be, okay, things like that. It was actually a pretty math-based science. And then those stars were then later targeted with our telescopes finding all those extrasolar planets. Okay, so like I said, if the source is moving, the waves bunch up in front of it, the waves spread out behind it, so in front we hear a higher frequency, okay, and in the back we hear a lower frequency. Anytime the source is going away or retreating, the frequency observed will be lower. Anytime the source is approaching, the frequency observed will be higher. Okay, all right, we're going to look at the formula here before we do anything else. So, formula for the Doppler effect. Yeah. Okay. So on your formula sheet, okay, we have F equals FO, and then okay, the actual formula looks like this. V plus or minus VO over V plus or minus VS. Okay? So this formula takes into account both a moving observer as well as a moving source. Since we're not dealing with moving observers, we're modifying the formula, okay, so that it looks just like this. V over V plus or minus Vs. Okay, so V is the speed of the waves. In this case, the speed of sound. Okay. Vs is the speed of the source. Okay, so whatever it is that's making the waves, its speed is Vs. Okay. This F here is the Doppler shifted frequency, or the frequency that is observed by the observer. FO is the original frequency. Okay, so it's the frequency that's actually being produced. F is the frequency that's being perceived. Okay, it's very important that you keep those straight. All right, in which situation would I want to use the plus? Because it says plus or minus. I've got to decide when I use plus and when I use minus. So should I use plus for approaching or retreating? Okay, think about this. If the object is approaching me, this number is bigger or smaller than this number? Bigger. Okay. If I want this number, F, to be bigger than FO, what's in brackets needs to be greater than what? 1. Okay, because I'm going to be multiplying FO by this number. Okay, so this, whatever's in brackets here, has to be greater than 1 if I want F to be bigger than FO. That means that if the object is approaching me, I actually want to subtract, because then the number on the bottom will be smaller than the number on the top. That gives me a number greater than 1, and I'll get F to be bigger than FO. If the object is retreating, then I'll add. This will come out to a decimal that's less than 1, and F will be smaller than FO. Okay, so you may just want to remember that or write that down. Okay, the subtraction is used for an approaching source. The addition is used for a retreating source. Okay. All right, now manipulation. Going to have to be able to manipulate this formula. It looks really complex, but in actual fact it's not. Okay? If I want to solve for FO, how do I manipulate this equation? Divide by the brackets. They take this whole thing over, right? I mean, the brackets say I've got to know what this number is before I multiply it by this number, right? So this is really just a number, and I can divide it over here. So if I want to solve for FO, okay, that's just going to be F divided by V over V plus or minus Vs. Okay, that's how I calculate that. Everybody okay with that? So it gets a little hairier if I've got to calculate something inside the brackets. So if I want to calculate one of the numbers in the brackets, and you're only going to have to calculate Vs. Okay, you won't have to calculate V. Why? Well, it actually doesn't cancel, but you have to factor it. Since we can't guarantee you taking math 20 yet, you don't have to do it. So you won't have to solve for V. Okay, you will have to solve for Vs. So if I'm solving for Vs, the first thing I want to do is bring FO over here. So I'm going to divide both sides by FO. Now, when I do that, that eliminates the need for the brackets. Okay, Vs is on the bottom. If I'm going to solve for it, it needs to be on the top. Okay, so rules of algebra say I can do whatever I want to an equation, as long as I... All right, so what I'm going to do is flip both sides. Okay, and then I'm going to move V over here by multiplying by. Okay, and then all I have to decide is am I adding or subtracting Vs? Based on that, okay, then I move the other V. So if I am, let's say, subtracting, because that'll be the tougher one. Okay, if I'm going V minus Vs, what I would do is add Vs over here, and then subtract this over to the other side. Okay? If I'm adding Vs, then I just subtract V over to the other side. Everybody with me on those? All right, so you're only going to be asked to calculate F, FO, or Vs using this formula, okay? Nothing else. Okay, I want you guys to try this one. So I got a train traveling at 30 meters per second. Okay, its whistle is making a sound wave that has a frequency of 224 hertz. You are standing, keywords, beside the tracks, not on them. Never observe a train from the tracks. Bad idea. Should stand beside the tracks. Okay. So what change in frequency do you detect for the pitch of the whistle? So in other words, what frequency do you hear instead of what one is actually produced? So we're looking for what frequency you hear based on this information. Speed of sound is 330. I'll give you a couple minutes on that. Okay, so let's have a look at this one. We don't have to manipulate the formula for this one. So we're solving for the perceived or Doppler shifted frequency. Okay, so we're looking for F. Okay, we know what FO is. Okay, we know that we have V. And are we adding or subtracting here? We're subtracting. It's as the train passes, so it's moving towards me. Okay, so that's V minus Vs. All right, so all I have to do is plug in my numbers here. So that's going to be 224, the actual or original frequency, multiplied by 330 over 330 minus 30. Okay, so we're going to have 224 times 330 divided by 300. Okay, so the frequency that we hear will be 246 hertz. Okay, which makes sense. It's higher than the original frequency, and that fits with the object approaching us. Okay, questions on that one? I want you guys to try these two here. Okay, so for question number one, okay, we're crossing a crosswalk, an approaching driver blows their horn. Okay, the true frequency is 264 hertz. All right, that's FO. Okay, the car is approaching at a speed of 60 kilometers per hour, which needs to be converted to meters per second. Okay, that's the speed of our source. Okay, so if we take 60 and divide by 3.6, okay, we're looking at 16.67 meters per second. Okay, we also know that the speed of sound is 340 meters per second. So that's the speed of our waves. Right? So we don't have to manipulate again. It's just a matter of plugging in the numbers. So 264 times, okay, 340 over 340 plus or minus? Minus. Okay, 16.67. Right? When we do that, we should get 278 hertz. Okay, again, a larger frequency than the actual one because the car is approaching us. Okay, how many people have done number two? No. No? Okay, give you a few more minutes on number two. All right, so on number two, okay, we are looking for the actual frequency of the sounds. Okay, so we have the perceived frequency to be 512 hertz. Okay, so that's the sound we hear. Okay, we know that the speed is 360 kilometers per hour, so that's 100 meters per second. Okay, and we know that the speed of the waves is 345 meters per second. All right, so F equals FO, and then we're going to be multiplying by V over V minus Vs. The source is still approaching. If I want to find FO, I just divide the entire bracket over to this side. So V over V minus Vs comes over here, okay, and I'm solving for FO. So we'll have our 512 hertz divided by 345 over 345 minus 100. So 512, okay, divided by 345 divided by 245. Okay, so we're looking at a frequency. The actual frequency is 363 hertz. Okay, so quite a bit lower. Okay, sorry, 364 rounds up, right? Yeah, 364. Okay, hertz. All right, making some sense there. All right, you will definitely get a Doppler question on Wednesday's unit exam. Okay, you'll also get one of those two-speaker questions and some wave property stuff and pendulum question and a mass on the spring question, right? And some conservation of energy and Hooke's law. Okay, at least some of all of that on there. All right. Okay, I want you guys to try number 4. You don't have to do number 3 because number 3 is finding the speed of the waves, which you don't have to do. Okay, don't do number 3, but try number 4. So on number 4, train is moving away from us. So am I adding or subtracting? Adding. Okay. The frequency of its whistle is determined to be 475 hertz. That's the perceived frequency. Okay. The actual frequency of the whistle is 500 hertz. If I was confused, would I be able to figure out which one was which? Yes, I would. Okay. An object moving away, I'm going to perceive a lower frequency. So if you're ever confused by the wording of the question, if you saw away, F is smaller than FO. Okay? All right. And we know that the speed of sound in that air is 350 meters per second. All right. So we are looking for the speed of the source. So we're looking for Vs. So we have F equals FO, and then we have V over V plus Vs in this situation. So first I'm going to bring FO over to the other side by dividing by it. Okay, then I'm going to flip both sides just so I can get Vs on the top. So I'll have FO over F equals V plus Vs over V. Okay, and I'm going to multiply both sides by V, and then I'm going to subtract V. So what I'll be left with is FOV over F, okay, minus V equals Vs. Okay, that's my manipulation of solving for Vs. So when I plug in my numbers here, okay, that'll be 500 times the speed of the waves, 350, divided by 475. Okay, and then I'm going to subtract 350, okay, and that'll give me my speed of the waves, or sorry, speed of the vehicle. And so 500 times 350, right? No. Yes, 500 times 350. Okay, then divide that by 475. Okay, and then I subtract 350. All right, so the thing was moving at 18 meters per second. Okay. Everybody with me on that one? That's about as tricky as they get. Probably should know how to do one of the tricky ones, because it might spoil what the only test.
So this one?
Okay, maybe. All right, so I'm going to put up some Doppler effect questions up on the board here. They're from the workbook. That's what I want you working on the remainder of class. If you're having trouble with any of them, let me know so we can go through them. Okay, but I'll put them up here, and then that's what we're working on. Okay, 1 through 8, they're all moving source questions. Okay, so let's get working on those. Okay, so let's have a look at number 3 here. So the trick with number 3 is just to pick two frequencies that are 3% apart. I like 103 and 100 because they're 3% apart. Okay, that's the best bet. Right? So how fast does the source have to be moving so that the observed frequency is 3% higher? So this is going to be F, this is going to be FO, okay, and then the speed of sound is 340 meters per second. So I'm manipulating for Vs, and the only way for this to be higher is if I'm subtracting its approaching. Okay, so I'm going to have F equals FO V minus Vs. So when I manipulate all this, I'm going to have FOV okay, over F equals V minus Vs. Now I want to solve for Vs, so I'm bringing Vs over here by adding it. Okay, that leaves V over there. Then I'm just going to subtract this whole thing over to this side. Okay, that's going to leave me with Vs. Okay, so Vs will be 340 minus 100 times 340 over 103. Okay, and when I do that, I should get 340 minus 100 times 340 divided by 103. Okay, so it has to be moving at 9.9 meters per second. All right, any others giving us trouble? Okay, keep going then.